Hello GTS 300 and welcome back to the fifth lecture, and today we're going to be focusing on probability. So today I'm going to be setting the fourth assignment for you to carry out, and that's going to be on probability. I think the key point for me to emphasize is that we're going to be kind of wrapping up this first third of the course over the next week or so. So this is basically the last part of that section of the course. So let me just show you the syllabus. You remember that you have this document available to you. And that we've basically been through week 1, week 2. So week 1 was on the introduction, week 2 was basic data and geographic data, week 3 was descriptive statistics, week 4 was descriptive spatial statistics, and here we are today focusing on probability. I would say that probability is probably one of the most kind of dense lectures that we have throughout the term, so it's quite a lot of information. This is probably going to be a fairly long video, and there's probably quite a lot for you to go over, unfortunately, but just stick with me, take a break if you need to and come back to the video, but do make sure you kind of cement these core parts of the course into your memory, because today probability will be building on the kind of descriptive statistics we covered previously, and then as we start to move into the more kind of complicated parts of the course, so the inferential statistics part is going to be building on a lot of the probability understanding that you're going to gain from today. So all of this information is cumulative. Please make sure that you kind of keep up week to week, and then I'm sure you'll be on a really positive path in order to succeed on this course, okay? So the midterm's going to go live next week, so what I'll do is I will give you a lecture next week, and the midterm will be set, and there'll basically be a number of kind of midterm tests which I want you to carry out, and those tests are basically going to test you on the knowledge that you have. They should be fairly straightforward to undertake, but it's going to tell you what you do or you don't know, and it's basically essential that you carry those out before you take the midterm in order for you to actually succeed, okay? Because it's going to give you a good understanding of kind of what I'm looking for, what I expect you to know, and all those areas that you don't succeed on the kind of unmarked tests, sorry, the ungraded tests, then they will kind of direct how you need to kind of put your focus for the actual midterm, okay? And then hopefully you'll all be performing really well on that part of the course. And remember, you've got the marking guidelines for how that plays out within the syllabus. And I think, if I recall correctly, it's something like 25% of the overall mark, yes, on this first midterm exam. So it's important that you do well on that, okay? Great, reach out to me if you've got any questions. Today we're going to be focusing on probability, as I've already said, so let's dig into some of the content. Okay, so if we look in the dictionary, the Oxford English Dictionary, for example, that is going to define probability as basically the chance or the likelihood of some sort of outcome actually occurring, okay? And the key point here is the word kind of chance or likelihood, which is probabilistic, okay? It's probability based. It may happen, it may not happen. This is obviously kind of a qualitative description, but we're actually able to use quantitative numbers in order to kind of understand how these processes play out, okay? Now, a lot of maybe what we've covered already or kind of discussed in other parts of the course focus on deterministic processes. So what are they? Well, essentially within the spatial sciences, when we talk about deterministic spatial processes, we're talking about those phenomena that can basically be predicted with a large degree of certainty, okay? So there's no kind of element of randomness within them in order to kind of determine their future states. So if I told you that I wanted you to go out and you're an engineer and I told you to design a bridge, or if I told you, as an astrophysicist, I wanted you to plot future planet movements, well, you could do that using Newtonian physics fairly easily, and there wouldn't be any sort of randomness, there wouldn't be too much randomness in the results that you would get, okay? And often this kind of contrasts with what we might see in most of the spatial sciences that we evaluate here, particularly the parts where there's human involvement, because the minute you get human involvement, then there's not going to be quite so much predictability within those types of methods, okay? So the deterministic process has no randomness in the determination of future states. And lots of examples of these deterministic processes could be the movement of the planets, models of the Earth, so for example our seasons, daylight hours, nighttime hours through the year on a day or a monthly basis, or the behavior of waves. Okay, so if we look at Maxwell's equations, that's how light behaves, radio behaves, ultrasound behaves. They're all part of that electromagnetic spectrum. They just have very different frequencies, all of those different parts of those waves that are used for these different applications. Okay. So we don't have many examples of deterministic examples in kind of spatial sciences, so I'm using a physics-based one here. So this is the electromagnetic spectrum, and this is essentially, you probably studied this before, this is all the different kind of wavelengths and what they can basically be used for. So they're categorized here. So obviously we're very familiar with radio, and you use that on a daily basis. You know, when you log onto your cell phone, hourly basis, probably all of that data is being transferred using packets, so packets of data that are placed onto radio waves and transferred to you. Or for example, just me talking now, I'm producing sound waves. And that is obviously one particular kind of frequency range within that whole spectrum. Okay. So if we actually wanted to predict sound wave levels or cell phone signal based on distance in controlled experimental conditions, we could easily do that because these are kind of deterministic processes which we can mathematically model, right? So if we set up an experiment and we decided to shout at different volumes, providing there was no outside interaction, we could measure that, and we would be able to kind of determine how the properties of those waves from us shouting at different levels would kind of translate into different maybe reverberation patterns or something like this, and that would all be kind of nicely predictable. It then contrasts with most of the processes that we actually deal with in spatial sciences, because humans are often involved, which contain this kind of element of uncertainty. Okay, so there's two different types of probabilistic processes which we're concerned with here. So number one, these are random processes. So we've dealt with these before when we were thinking of, we're focusing on rolling a die, or rolling a dice, or rolling two die, as we did in the previous descriptive statistic lectures. That is a random process, but there's actually kind of few geographical examples of where those processes are going to play out in a truly random way. Okay, so most of what we deal with in spatial science is basically stochastic processes. All right, so this is where you have like maybe half of the explanation within that process being kind of deterministically expected, and then you have half which is basically a random component. Okay, so the likelihood of these outcomes can be specified, but not all outcomes are equal. A good example here is hurricane trajectory modeling. Okay, so I've used this quite a few times now, but just think of what the word stochastic, what we mean here is basically something that is semi-random. Okay, so it might have a predictable component and then it has a random component that adds on the end, which causes some sort of uncertainty that you can't always model really well. You might be familiar with this type of methodology that you may have heard before, Monte Carlo simulation. So this is basically where you can use this as a method to model stochastic processes, okay? And it has its roots. It wasn't originally invented, but it was used quite heavily within the Manhattan Project, so the Los Alamos laboratory during the end of the Second World War, during the nuclear program, and Monte Carlo simulation kind of came into its own following that kind of expansion of modern computing, essentially. So you could use Monte Carlo as a way to generate lots of different kind of random outcomes, and then you can quantify those outcomes in a different way, and that can be useful to understand stochastic processes. Okay, so over here we have the deterministic process part, and over here we have the random process part, and in the middle we have the stochastic kind of blend between these two different approaches. So let's get into kind of the nuts and bolts of probability then. So that was all very qualitative before, but let's focus on maybe how we kind of actually estimate what the probability is for something, for example, outcome A. So P of A here denotes the probability for A actually occurring. So you can see P of A here is equal to F of A, so the absolute frequency for a particular outcome, divided by F of E, so it's the frequency of all of the outcomes. Okay, so don't worry if that doesn't mean anything to you yet. I'm going to explain it to you in very clear terms and give you lots of examples. But as this is a probability, this PA value here is going to basically be between 0 and 1. Okay, And essentially, a good example of this would be if we were to roll a dice and we were actually to get a 6. The probability of that would be 1 over 6, so we'd be dividing 1 by 6, which gives us 0.167, which if we multiply by 100 to get the percentage likelihood, we get 16.7. Okay, so we're just moving the decimal point 2 places to the right in order to get that percentage likelihood. Or what we could do is we could consider the number of wet or dry days. Okay, so let's assume that we have 100 days and we have 38 of them wet, 62 of them dry. And then maybe I pose the question to you, well, what would happen if we wanted to estimate the probability of a wet day? Okay, so P of W here, the probability for a wet day is equal to the number of wet days over all of the total days. Okay, so the number of wet days, the absolute frequency for wet days is 38. That should be fairly clear to you. We've got 38 wet days. And then we need to divide it by the frequency for all outcomes. Okay, so if we've got 38 wet days and 62 dry days, that's 100 days, which means that we have 38 divided by 100. And when we do that, we get a probability of 0.38 of getting a wet day, okay, which is equivalent to 38% if we multiply it by 100. Okay, so hopefully that's starting to be more clear to you now. So basically the relative frequency is defined as the ratio between the absolute frequency of an outcome and the frequency of all of the outcomes. So that's basically what we're obtaining here. When we talk about the absolute, that's basically the actual number of times an outcome occurred in the kind of the raw units, as you like. Whereas if we talk about the relative frequency, this is where we convert it to a frequency related to the overall number of event outcomes, okay? So what we end up with is all of the relative frequencies that we've calculated adding up to 1 if we focus on the probabilities between 0 and 1. Or maybe if we convert this, we multiply these values by 100 and we consider them as percentage likelihoods. Obviously, if you've got a coin and it's 50% heads and 50% tails, then they add up, all of those outcomes add up to 100, right? Okay, so that's that you're getting when you say 50%, you're getting the relative frequency in relation to the total number of potential outcomes, which obviously is going to be 100 if you're dealing in percentage terms. So the relative frequency can be determined based on an approach which uses the law of large numbers, all right? So the size of an experimental data sample has a large impact on the estimation of the relative frequency. So if we toss a coin and we know which side of the coin lands upwards, whether it's heads or whether it's tails, we can't actually predict which outcome it's going to be, whether it's heads or tails, at least not with certainty in advance. But we are able to understand the probability of which outcome it could be, okay? So we could toss the coin again and again and again, and the proportion of the heads and the tails, eventually through the law of large numbers, would converge on there being approximately a 50% chance for a heads and a 50% chance for a tails. So let's suppose that we set up an experiment where we repeat this indefinitely under a set of kind of fixed conditions. And we suppose that during the number of sample repetitions, so n repetitions, a certain event occurs with frequency f. So the ratio basically to get the relative frequency would be f over n. So the Fn approaches a fixed value that values the probability of an event. Okay, so if all that's kind of gobbledygook, then let's focus on this table that we have here, which basically provides an iterative understanding of the number of coin tosses that we have, the number of heads that we're going to obtain, and then the relative frequency by dividing those two different metrics that we get. Okay, so if we start with the number of coin tosses, let's say there's just 10, we might end up with 8 heads, and we would end up with some relative frequency here of 0.8. So we'd say there's an 80% chance of getting heads, which obviously is wrong, it's incorrect. And we know that a priori because we know that a coin has 2 possible outcomes and therefore there's a 50% chance of getting each. And the issue here, of course, is that we've got a very small sample size. So what we want to do is we want to keep increasing the sample size. So as we go to 100, we might get 62 heads. And then we get a 0.62, so 62% relative frequency. And then we can kind of increase this each time. So let's say we go to 1,000 or 5,000 or 10,000 tosses. As we do that, the number of heads starts to converge broadly on the kind of the expected half value that you would assume. Okay, so you can see here that what we end up with are values that converge towards a 50% likelihood of there being a heads, or a tails if we iterate over all of these many times. So I spoke about the use of Monte Carlo in the Manhattan Project, and you can imagine before this, if you weren't able to use a computer, it would be very hard to actually manually carry out all of these individual experiments individual trial runs in order to get 20,000 values. But if you can use a computer to do that, this is kind of one of the revolutionary examples of using modern computing. Well, then you can generate all of these, on a modern computer in literally a fraction of a second, okay? And that provides us with a very kind of strong probabilistic understanding of what the outcome would be, the relative frequency of some particular outcome that we're interested in. And this is kind of the most simple way to understand this, but you could apply this, in more complicated terms to whatever you wanted, whether it's hurricane tracking, or whether it's the number of tornadoes that might actually hit Florida a year, or whatever. Sorry, number of hurricanes that might hit Florida per year. Okay, so let's think a little bit about some of the terms and definitions around probability. So I've kind of thrown a few of them out already, but essentially, let's say we wanted to go out and we're going to roll 2 die in order to understand the probability of getting different outcomes. Well, that would be an experiment, so that's a set of procedures which gives rise to particular data that we want to obtain. And then let's understand what the sample space is. Okay, so this is basically all the possible outcomes that could occur. So this is, if you rolled 2 die, then you would end up with a sample space that would consider every possible outcome out of those 2 die. So it would be 1, 1, 1, 2, 1, 3, 1, 4, and going all the way up until you get, 4, 6, 5, 6, 6, 6, and then you get all of that total sample space. Now within that you can get an elementary event, which is just an individual outcome from the sample space, so something that could possibly occur. A trial is basically each time that you might run that experiment, so it's each action that you take, so it's each time that you actually roll the die. And then the outcome is one or more of the elementary events in an experiment. Okay, so let's just think this through. So in terms of what this example here, an experiment, so let's say it's the probability of getting at least 1 6 while rolling a die twice. So your sample space is going to be all of those possible outcomes that you could potentially get. Your elementary events are going to be basically all the outcomes, all of the the sample space is the set of all possible outcomes, whereas the elementary events is an element from the sample space, so something that could possibly occur. The trial would be rolling the die twice, and the outcome would be actually getting some sort of outcome. So sorry, this is rolling a single dice twice, not 2. Okay, so I didn't mean to confuse you there. But you get the point there, right? Which is that we have these different type of definitions, and you kind of just need to learn them, unfortunately. So let's think of the second one here. The probability of basically there being more than 60 inches of annual precipitation. Well, the sample space would be any number that's over 0, okay? So that could be infinite here because it's a continuous variable. The elementary space would be any event that's basically over those 60 inches of annual precipitation. The trial would be each year within our record, and the outcome could be, for example, 63.5 inches, which is maybe the outcome that you got for one of these years that triggered that particular level. Now, there are certain rules of probability, and I'm going to walk you through a variety of them. There's basically 3 main ones that I need you to learn, which is how you do the calculations for probability for particular outcomes. So remember, probabilities run between 0 and 1, so the probability of A here, P of A, will be between 0 and 1. And essentially, what we can obtain if we know the PA value here, which let's say is 50%, we can actually obtain the reciprocal, so what's the probability of all the other outcomes that could occur if we know that this is out of 1, right? So if P of A is 0.5, it's 50%, we can subtract that value from 1, and it must mean that the probability of getting the reciprocal, so all the other values, is basically 0.5, okay, so it's 50%, because you know that it's going to be within this total number of outcomes. Okay, so we can characterize these different events based on these 3 outcomes. So, statistically independent events, mutually exclusive events, and non-mutually exclusive events. And I'm going to walk you through exactly what these mean in these following slides. So, statistically independent events, these are important to understand and they will come up later in the course. So this is where one event does not influence another event. Okay, so if I flip a coin, the second time I flip the coin, it is not dependent on the first time that I flip it. Okay, so these are entirely independent events. So what if we want to calculate the probability of two statistically independent events? Well, then essentially what we're able to do is we're able to multiply the probability together in order to get the probability of these two statistically independent events occurring. So the probability for A and B is equal to the probability of A multiplied by the probability of B. What is the chance P of flipping a head and then a tails in order? Okay, well, we're going to work this out now. So just bear with me and then I'll give you a graphical understanding of this on the next slide. So the probability of it being heads and a tails in two consecutive trials is basically the probability of it getting a heads multiplied by the probability of the coin being a tails. So if we know that it's 0.5, so a half for a heads, and we know that it's 0.5, a half for a tails, and we multiply them together, and what we get is a quarter, and that's basically 25% chance. Okay, so 50% chance of a heads multiplied by 50% chance for a tails, and we get, as a consequence of those outcomes, a 25% chance for flipping a head and then a tails in order. And the key point here is with the word "and," because it indicates that these are statistically independent events. Okay. Right, so the rules of probability. So P for heads and tails, so this is basically just the equation that I showed before, so it's the probability of getting these outcomes. Let's think of it graphically like this. I know I didn't always take to equations the first time someone showed it to me, so here I just want to kind of graphically show you how you understand this, and then you can either look at the equation and understand it if that's how you like to view the world, or you can look at the graphic as I'm showing, and then hopefully that will kind of trigger what we're talking about here in more depth. So we're going to start here on the first flip, and we're going to end down here on the second flip. Okay, so this is flip 1, this row, and this is flip 2. When we start, we have a 50% probability 0.5 of flipping a heads and a 50% probability 0.5 of flipping a tails. Okay, so that's how we get to our first stage of the experiment. And then once we have that, we need to flip again. Okay, so to get heads followed by heads, it would be, we would need to go down this path here on the right. So it would be 0.5 to get here and 0.5 to get here. When you multiply those together, you would obviously get 0.25. Okay. And then you can follow that all the way across this individual event space. So these are all the different event outcomes that we could possibly get. And obviously, because there's 4 outcomes down here and there's 100, we know what all the probability is going to add up to 1 based on following this event tree through. We know that they're therefore going to be 0.25 each, or we're going to have a 25% chance each of landing at any of those 1 finishing points for those 2 flips. So don't worry, we'll start to go over this in the lab if it's still not clear, and then you can kind of reinforce it, and then we'll cover that when we get to the actual assignment as well for you to kind of have a go on your own. So they were statistically independent events where we had the word "and" within the actual question. Here we've got mutually exclusive events, okay? So this is where we have no overlap between the events. The events cannot appear at the same time. And the question here is, well, what if we want to calculate the probability of 2 mutually exclusive events occurring? Okay, so let's see what the probability of A or B. So the difference here is not "and" like it was before, indicating that they're kind of going to be sequential events. This is "or", so it's that you can't have one or the other at the same period of time. And rather than multiplying like we did previously, here what we're going to do is we're going to add the probabilities together. So we're going to get the probability of A and the probability of B, and then the mutually exclusive probability of getting either of those is going to be the summation of those probabilities. Okay. So let me give you a dog-focused example as ever. So what's the probability of picking a Labrador or a Golden Retriever from the statistical data which we've got down here? So we've got dog breeds here on the left-hand side and quantities on the right-hand side. So we've got 4 Labradors, we've got 2 German Shepherds, we've got 2 Golden Retrievers, we've got 1 Bulldog, and we've got one Poodle. So we've got 10 dogs and we've got 5 different actual breeds, okay? So what's the probability of picking a Labrador or a Golden Retriever? Okay, so we want the probability of a Lab or a Golden Retriever, which means we need the probability for the Lab. Well, okay, that's going to be 4 Labradors out of 10, which means it's going to be 4 out of 10. And then we're going to have the probability for the Golden Retriever. So we've got 2 Golden Retrievers out of 10, so that's the probability there. So this is going to be 0.4, and this is going to be 0.2. And we're going to add them together, and what we get is 6 out of 10, or in probability terms, 0.6, which obviously equates to a percentage likelihood of 60%. Okay, so I think the key point here obviously is that we use the word or, which means the pick is successful if either of the 2 conditions is met. And this calculation works because basically you can't simultaneously be a Labrador or a Golden Retriever at the same time. Okay, so these are mutually exclusive outcomes. The problem is often that you might have non-mutually exclusive outcomes, okay, which means that it's possible to overlap in the different categories of data that you might have. So what's the probability of picking a Labrador or a black dog? In here I've slightly changed the data set, so we've got our dog breeds as we had before. We've got Labradors, we've got German Shepherds, Golden Retrievers, Bulldogs and Poodles. And then we've got colours, okay, so the colours are, we've got 2 black Labradors, we've got 2 yellow Labradors, we've got just 2 German Shepherds which are tan, 2 Golden Retrievers which are obviously golden, and then we've got a white bulldog and a black poodle, okay? And the point here is that you could simultaneously be a Labrador, and you could, you could be a Labrador, or you could be black, but we don't want to include the part of the probability where you could be a Labrador and black, right? Because we want to exclude that from our calculations. So what's the probability of actually picking a Lab or a black dog? Well, then what we need to do here is we need to get the probability, which is going to be based on having the probability of it being a Lab, which is going to be 2 over 10, and the probability of it being black, which is going to be 3 over 10, because we also have this black poodle here. And then we're going to need to subtract the probability of something being both a Lab and black. Okay, so that's this one here, which is 2 out of 10. So what we end up with, the first summation is 7, and then we need to subtract the mutually exclusive events here, which are the Labradors, which are also black, which are 2 over 10, and therefore to get the non-mutually exclusive outcomes, we have 5 over 10, or 50%, okay? So that's the equation if we've got these non-mutually exclusive events, and hopefully those 3 types of approaches towards calculating these probabilities are fairly kind of clear in a theoretical sense now, and then I'll cover them within the lab work. Okay, so we'll look at how we calculate those in a little bit more detail, and hopefully that will kind of drill it into your mind, and there will be some questions on that within the assignment that you need to kind of piece together. So you need to be able to look at the question and say, right, what's the question asking me here? Are these events mutually exclusive? Are they non-mutually exclusive? Are they statistically independent events? And then you need to work out what the right approach is going to be. Okay, so whether you should be adding those probabilities, whether you should be multiplying those probabilities, or whether you should be adding them and then removing any mutually exclusive outcomes. Okay, so look, that's the first part of the lecture. Now we're going to move on to basically the second part, which could be a little bit more kind of arduous for you. This is kind of more advanced material, but just bear with me because it's a really exciting set of tools, and I think that it will set you up nicely if you're able to understand the use of probability distributions. So the probability of an outcome in certain problems follows very consistent patterns, which is really handy, because in statistical terms, if you know what the shape of the pattern is going to be, then you can basically use that to your advantage, right? So this pattern here is called a probability distribution, and it will influence the type of outcomes that you're going to get when you study that phenomenon. So it's closely related to a frequency distribution, right? And you remember that we did frequency distributions before when we plotted histograms. And as a consequence, we can kind of think of these in the same way. It's just a slightly different interpretation. So a probability distribution is defined as a table, graph, or mathematical function that describes the potential value of a random variable and their corresponding probabilities. So when we think about the frequency distribution, this is basically I'm going to use a fancy Latin word here, ex post. So this shows the kind of past number of occurrences that we've got. So maybe after we've carried out an experiment, like we roll some die, we'll end up with the frequency distribution for all of the outcomes. And that's kind of looking backwards at the outcomes that we got. It's ex post. And then that kind of contrasts with probability distribution, where we can kind of, if we repeated that experiment continually and then we kind of understood what the shape of that distribution was going to be, well, then we could actually think of this less about what the past results have been and more about what the potential values might be in the future, and actually use that frequency shape as an indication of the probability of occurrence for certain values at a future point in time. So this is all very kind of statistical, very econometric, kind of backward looking, but then there's also this kind of really nice scientific aspect here of, well, let's use these probability distributions to also think about future outcomes, and that could be prediction, which is a hard thing to do, it could be forecasting, but these are kind of the fundamentals for science, both within kind of the natural sciences, but also these are widely used within econometrics, for example, if you think of all of the economic forecasting that takes place, and other fields that use, you know, quantitative math approaches across science, technology, engineering, and mathematics. So this is really cool stuff. So I really want you to learn and understand what we mean when we talk about probability distributions. So I'm going to go back to my favorite example, which is that we've got these two die that we've rolled over and over again. We've carried this experiment out 100 times, and we end up having you know, the summation of those outcomes, the middle point being 7. So this is basically the mean, the median, and the mode, and that's because we've got a normally distributed set of data. And basically, we're using the probability of this outcome here. We could empirically derive this data, so we can carry out this experiment, and it gives us this shape, and that's great. But then we can think about this also in terms of the probability. So when I was pointing to the y-axis here, this is the probability of any type of outcome. Okay, so you've got a 16% probability of rolling a 7. Okay, because the probability is 0.16. Or if you think, okay, what's the probability of getting, you know, the summation of 2 from a single roll? Well, it's going to be down here at about 2%. Okay, so it's a really low amount relative to the rest of the distribution. Which is why, if you're playing Monopoly, you should always consider those properties that are, you know, 6, 7, or 8 steps away from jail. Okay, and that's because most people are going to have a high likelihood of going to jail at some point, and then they have to escape from jail, and then they're going to have a high probability of basically rolling these outcomes here, so 6, 7, or 8, and therefore it makes a lot of sense to build properties and hotels in that area of the board. Okay, great. So there are 2 different types of probability distributions that we're going to focus on here. So we have discrete outcomes. So we covered this before. Discrete data are where we have integer values. So if we talk about people, that's going to be a discrete outcome because you can't have 1.5 persons. Okay, you can only have 1 or 2. The same for hurricanes. You can't have half a hurricane. So it's a discrete outcome. You're going to have 1 hurricane or 2 hurricanes or 3 hurricanes. Okay, and we can use the binomial or the Poisson distributions here in order for us to understand these types of probability distributions, and I'll explain what they mean as we run through this lecture. And then finally, we're going to return to the normal distribution, so one of our favorite types of distributions for continuous data, the bell-shaped curve, and we're going to focus on developing z-scores using that normal distribution shape, which allows us to think probabilistically about the outcomes that we might get in the future from those types of phenomena that basically produce a normal distribution, okay, like the ones I've shown before. So rolling 2 die and then actually summing the outcomes, okay. So let's start on binomial distribution. So a discrete probability distribution with only two outcomes. So the trick here is in the name, right? So binomial deals with trials that consist of either or outcomes. Okay, so there's only two outcomes. So the example is that a person is either employed or unemployed. You know, a river is either above a set level or below a set level. And the respondent to an opinion poll is either in favour or opposes a particular issue. So just imagine that we have a sequence of outcomes which can only take one or two values. So yes, no, true or false, success, fail, 1 or 0. So just think of this as you know, I like to think of it in terms of the kind of semantics of the word. So bi is indicative of there being two. So you think bicycle or binoculars. So the binomial distribution is a distribution focusing on just two individual outcomes at a time, okay? So this occurs when we have the following conditions. So there are repeated trials where you can only have one of two outcomes. So this is why it's useful in engineering, because you can have fail or success, or useful in spatial sciences or environmental sciences, because you can have either rain or no rain. And the probability of one given outcome is always going to be constant, and it's denoted by the letter P. And the complementary probability, which we discussed before, is basically going to be the letter Q, so we can get the complementary probability. We've covered this before. If you know the probability is 50%, you can subtract 0.5 from 1, which is the total number of outcomes, and you're going to get 0.5, so 50% for the other outcome or outcomes. Okay, so we can do that here. Q equals 1 minus P. Okay, or we could add it together to find the total number of outcomes, which would be P plus Q. All right. So when you think of it in these terms, there's really only two components, the probability and the complement probability, and they both add up to the full event space. Okay, the full total number of probabilistic outcomes. Importantly, the trials are independent, and I'll come back to this as we start to move through the course, because it's one of those assumptions which people may, when they start to use statistical tests, actually violate, and that's really bad because it means that you're basically producing junk results. So it's garbage in, garbage out with your statistical models. And then also the number of trials is denoted by the lowercase letter n, okay, for the sample size. And the outcome then follows a binomial distribution based on the parameters p and n. Okay, so this is going to be, really horrible for anyone who doesn't really like looking at math, but I'm going to break it down really easily for you, and I'm going to give you loads of help as to how you calculate this outcome using this equation, okay? So P of x is the probability for a given outcome occurring x times in n trials, okay? So x here is the number of times the given outcome takes place, so the success within n trials. N obviously is the number of trials that we're going to run. P is the probability of the given outcome that we know a priori, so before we even start running the trials. Q is obviously going to be the reciprocal of the probability, so Q is 1 minus P, the probability. So it's the probability of the other outcome that could take place. So if we're focusing on the probability of the success and the being P, then Q is going to be the probability of failure, okay, the opposite outcome. And then this here, this exclamation mark indicates that this is a factorial. So I'll just give you an example here for n. If the number of trials that we have is 5, then the factorial of 5 is going to be 5 times 4 times 3 times 2 times 1. Okay, so that's what we mean by factorial. We're able to multiply through the total number of trials that we've got to get the total number of permutations. So 5 times 4 is going to be 20. 20 times 3 is going to be 60. 60 times 2 is going to be 120. And 120 times 1 is going to be 120. Okay, so for those 5 different trials that we have, we're going to have 120 potential outcomes, okay? And we're able to capture that using this factorial approach. Okay, so it's just going to count the total number of possible permutations. Okay, so maybe I used the wrong word there saying outcomes, but possible permutations. So you can think of it like an event tree, like I showed you when we looked at rolling 2 consecutive die. So in the first one, we ended up with heads or tails, and in the second flip, we ended up having, you know, a set outcome, whether it was you know, another heads, so you get two heads in a row, or do you get heads and then a tails, or do you get a tails and then a heads, or then a tails and then tails? Okay, so you can think of it as a permutation as each part through that event tree. So hang on with me here, we're going to work through an example of how we use the binomial distribution. So you are looking to start a business and you're a vegetable grower and you're looking to basically buy or rent some land, and you need to select a site that's going to provide you with enough rain. So irrigation is going to be really important, and it's going to be expensive for you to use in those years where you don't have enough rain. Okay, so the grower can actually only afford to irrigate that part of the business, so that one site, 1 year in every 5 years. So that's when you get, you know, a really dry summer and there's not enough rain and to actually kind of water the plants, and then you have to irrigate yourself in some sort of ways, and that's going to be very costly. So one potential site that's being evaluated had enough rain for 21 out of 25 years. All right, so we've got the total number of outcomes where we had where we had rain, which is 21. We had the total number of years that this occurred over, which is 25. So we can get the probability for this, which is basically 4 years out of 25 required irrigation, right? Because there wasn't enough rain. So what we have here is enough rain in 21 years. We're interested in how many years there wasn't enough rain and therefore required irrigation. So therefore it's you know, 25 minus 21, which is 4, and then 4 divided by 25 for the total number of outcomes, and that gives us this 16% probability of irrigation being required. Okay, so the probability is 0.16. So the question therefore is, well, what's the probability that this grower can actually meet the requirement for irrigating only 1 in every, 1 year in 5, okay? So I'm going to provide you with this spreadsheet. I'll upload it so that you can have a look at this, but essentially here's a binomial example for how we calculate that. So we know that we've got 5 years we're interested in, that's what we want to run across these calculations for. Okay, so what's the probability that the grower can meet the requirement for irrigating only 1 in every 5? So that's the total number of trials that we're going to carry out. And then we're going to take this, this x outcome. So this is going to be the number of times the given outcome occurs. And then we're going to basically get the probability, which we've already got, which is 16%, or 0.16 here is the probability. And the reciprocal of that is 1 minus 0.16, so we get 0.84. Okay, look, so we've got n, x, p, and q. Okay, so now we've got everything that we need in order to calculate the probability of any x value. So we need to get the numerator, which means that we need to take the factorial of n here, multiply it by p to the power of x, multiplied by q to the power of n minus x. Okay, and when we do that, we get this numerator here, which I've calculated. And also you can do that for the denominator. So what we do is we need to get the factorial of x. So in each row here, it could be 0, 1, 2, etc. Multiply it by n minus x and find the factorial for that. So when we do that, and I've got the spreadsheet here that I'm willing to share with you. So we've got the n, which is going to be 5, the x values, which run down here. So this is just a similar example to what you have in the PowerPoint. And then we're able to calculate this numerator here, so we can get the factorial of a2, n here, multiplied by so C2, so it's this p-value raised to the power of this b-value here, multiplied by the d2 value, which is raised to the power of, so it's a2 minus b2. Okay, look, and you've got the same for the denominator, so we were able to get the 2, and then what we end up doing is we divide one by the other to get the probability of x, okay? And we end up with these probabilities down here. So the probability of us requiring no irrigation over that 5-year period is 0.4182, so it's about a 41.8% chance of requiring no irrigation, which is a good outcome because we don't have to spend any money on irrigating our field, okay? So we can just sell the crops. It means our margins are low, so our margins are higher because we've got fewer costs to consider. Okay, so the outcomes from that, you can see I've plotted them here, and you can look at this however you want to. But essentially what we end up with is these probabilities for no irrigation or 1 year's worth of irrigation. And remember that we don't have enough money to support irrigation for 2 or more years, okay? So we just want to find the probability for irrigating for only 1 year and 5. And to do that, therefore, what we need to do is we need to sum the probability here for no irrigation and for 1 year's of irrigation. For 1 year of irrigation, okay? And that will give us the probability that a grower can meet this requirement. So 0.418 plus 0.398. After rounding, that's basically going to be 0.8, which is 80% chance that basically we can meet this criteria, that we're able to irrigate for only 1 year and 5, okay? Which means that obviously you've got a 20% chance that you'd have to irrigate more than that. And I'm not a farmer, so I don't know if that's particularly risky or not. But I guess with climate change, particularly in many areas, there's going to be more drought around, and therefore this is going to become more of a frequent problem, which will mean that food prices will inevitably end up going up. And I've shown you this already from the Excel spreadsheet, which I'll share with you. So this is the probability of no irrigation being required, which is 0.4, 1 year's worth of irrigation being required. And then this is the non-viable point down here. So this is where we aren't able to support the actual site selection if we need that much irrigation. Okay, so without much further ado, let's move on. We can also find cumulative probabilities using the binomial. Okay, so if we flip a coin 10 times, what's the probability of getting more than 7 heads, right? So we need to find the probability of x being more than 7, which means we need the probability of x equaling 8 and x equaling 9 and x equaling 10, okay, because we only flipped the coin 10 times. So we need to find this probability here, and the way that we can do this, as I'll show you in R, is we can use this binom, which is the binomial function within R, okay? And there's multiple different ways that we can then use that function. So we can use the density function, so we find the probability of getting exactly x outcomes. We can use the cumulative function, which is the probability of getting up to x outcomes, which would be useful here. Or we can get the quantile function, so that finds what x value you get for a certain cumulative probability. Or what we can do is we can use a random function, so this tells us the number of successes in n trials calculated randomly. That's a lot of information. Don't worry, we'll go over it in the lab work. But just be aware that you're going to have these 4 different types of distribution functions within R, because I'm going to show you that this kind of repeats over all the different types. So whether it's a binomial or a Poisson or a Gaussian normal distribution, you have the same densitive, cumulative, quantile, and random functions for those 3 different, so 3 different distributions with 4 different types of prefixes that you might want to use to query those distribution types. Okay, so hopefully that didn't bamboozle you too much, and now we're able to move on to Poisson distribution. So this is where we have a discrete probability distribution with many outcomes. It's named after Simeon Denis Poisson, so it's French, from the late 18th, early 19th century. And essentially, these events are counted as whole numbers, so they're discrete. So these events, like a hurricane or a flood, you can't have half of one of those, so they're whole numbers. The event occurrences are actually independent of one another. So at least in mathematical modelling terms, from one season to the next, we consider flooding events as being independent. And that's fine to consider it that way. The reality is that there might be some residual effects if, for example, the level of a reservoir or something like this needs to be taken into account from one season to the next. But usually we treat these as independent events for flooding, for example. Assume that we have a fixed time interval or space when we're using a Poisson distribution, so a year, for example. The probability of an event has, within a certain time interval, basically does not change. Okay, so the probability is homogeneous over this time period. And the probability of observing a single event over a small interval is proportional to the size of that interval, which is important because you might be arbitrarily setting those time intervals, right? And then that's always going to lead to some sort of statistical problem. So you need to assume that there's some sort of consistent probability over those interval sizes that you set. And the probability of two events occurring in a small enough interval is negligible. Okay, so they're all the assumptions. Now let's think more about, well, what we can do with this. Well, Poisson distributions deal with those phenomena that basically occur randomly over space and time and can be measured in frequency terms. So this could be the days of school cancelled per year by school district, the number of park visitors per day into a particular park, the number of lightning strikes per area. So for example, in this diagram here, what we have are quadrats. So let's assume that these are 100 by 100 kilometer square areas, and we're going to refer to these as quadrats for sampling. Or maybe we could also think in example terms of the number of hurricanes actually hitting Florida per year. Okay, so it's like a defined geographic area. So quadrats, regularly sized square cells that cover a study area, right? So that's kind of what we're trying to describe down here, and we can use them as a way to kind of capture frequency events, and we can use Poisson-shaped distributions to understand this. So it's an easier equation this time round, I think, because it's only like 3 different components. But basically what we need to get the probability of x when using the Poisson distribution is we need to basically use the mean frequency of the event, which is this lambda term here, and we need to raise it to the power of the frequency of occurrence, and then divide it by, so we have the base of the natural logarithm here raised to the lambda value, which is the mean frequency of the event, multiplied by the factorial of x, okay? Remember, the factorial counts the total number of possible permutations that we could have. So the Poisson distribution characteristics. So the actual distribution is very good at describing rare events as they might take place, so car accidents or rare disease outcomes. And I've already mentioned before that they're discrete, and we're generally dealing here with mean frequencies, okay? So occurrences should be random, and technically you can have an infinite number of discrete outcomes. So, you know, maybe traditionally Mason only cancelled 2 days per, sorry, that should say 2 days per year. But, you know, there is the possibility that Mason cancels 10 or 25 or even 100 days per year. So imagine that these are not cancellations, these are just days where we don't come into campus. Traditionally, that maybe, you know, there were 2 days per year where due to snow we weren't all able to go into campus. Obviously, coronavirus is one of those rare events where actually everything was shifted online, and if you're going to use that particular approach, then, you know, maybe there were more than 100 cancelled days last year because we were basically doing remote learning for quite a substantial period of the year, unfortunately. So we will all look forward to being back in person in the classroom as soon as possible. So let's run through an example for using this Poisson distribution. So from 1900 to 2003, that's 104 years, Florida was hit by 24 major hurricanes. And the number of hits per year actually follows a Poisson distribution, okay? So what's the probability in this case that Florida will be hit by at least 3 major hurricanes in any particular year, God forbid? And the way that we do this is we run through that equation. So the probability of x occurring equals lambda raised to the power of x as the numerator, and then we need to find this denominator here, so the natural logarithm raised to the power of lambda multiplied by the factorial of x. And we can do that basically by saying, okay, the probability of x equaling or being larger than 3 is equal to 1 minus the probability of x being below 3. So we can basically say, okay, 1 minus the probability of no hurricanes hitting plus the probability of 1 hurricane hitting plus the probability of 2 hurricanes hitting will provide us with that one component, and then we can find the reciprocal overall. So how do we do that? Well, here we have each of the different values. So we know that if Florida was hit with 24 major hurricanes over 104 years, when we divide 24 by 100, we get 0.23, which is 23% chance of being hit by a hurricane in any particular year. and then we can raise it to, in this case, 0. This is focusing on there being no hurricanes hitting, so we have basically a 0.79 probability, 79% likelihood of there being no hurricanes hitting Florida. And then for one hurricane hitting Florida, when we run through this equation, we get 0.18, so 18% chance in any 1 year. And for 2, we get 0.02, so 2% chance of 2 hurricanes hitting Florida in a single year. So we can add all of those up. So 0.79 plus 0.18 plus 0.02 equals 0.998917. And when we take that from the total number of possible outcomes that we know will add up to 1, total number of the complete probability set that we have for all of these outcomes, then what we end up with is 0.00170829. So basically we have a 0.17% chance that Florida could be hit by 3 or more hurricanes in any particular year. Okay? So if that doesn't make sense, run through it again. Think here what we need to do is to basically calculate all of those values for all of those different types of event outcomes, and then basically add them together and then subtract them in order to get that final outcome. So you can think of this in terms of okay, this is just graphically the distribution, all right? So this is for the hurricane example. We can also think of this in terms of the number of school days cancelled for Mason. And finally, we'll be able to calculate that within R. And again, those Poisson distribution options are going to be based on calculating using the functions for density, cumulative probability, quantiles, or random occurrences. All right. So we'll go through that in the laboratory session. So the normal distribution. So this is a continuous probability distribution, which was first hypothesized and created by Gauss. So German. In the kind of what will have been the early part of the 19th century, essentially. This is the most common distribution that we use, and it's used for continuous types of data. And the key point is that with that bell-shaped curve, because it's symmetrical, it means that the mean, the median, and the mode will all overlap, okay? And I mentioned before that this is called the bell-shaped curve because it looks like a bell. The variance of this curve is going to be the square of the standard deviation. Okay, so the total area of all of the curve represents 100% of the possible outcomes. And what's really nice about this is we're going to be able to actually kind of think about this in terms of a standardized way of approaching distributions. So obviously we have the raw measurement data underneath, but then we're able to think probabilistically, so in relative terms, about how many data values are going to fall above or below a certain point. So since the normal distribution is continuous, the probability of any value is approximately 0, and we can find the cumulative probability of any particular outcome. So this could be, we could find the cumulative probability for a certain amount of precipitation in inches, or the fertility rate of a country. And the way that we're going to do this is basically by converting this into a standardized score. Okay, so it's called the Z-score, and this is a value in a distribution that we can. So for a value in the distribution, we're able to estimate the number of standard deviations that a value is above or below the mean. Okay, and this is really useful because it kind of abstracts away from what we're measuring in the kind of raw values, and then allows us to actually think in statistical terms, maybe even across different data sets, about the probability of an outcome. So we're really kind of generalizing away from the underlying data here. So to get this Z-score that I'm talking about, we need to basically use some key parts of the kind of statistical metrics that we've already generated previously. So to get this Z-score here for a normal distribution, then basically what we need to do is need to subtract the mean from the value that we've got for the numerator and divide it by the standard deviation. Okay, so this is for the population, obviously, because we've got mu here for the population mean. Obviously, we don't know what the population parameters are in many cases, so we will be more likely using the sample, which means that the mean for the sample is going to be x bar, So subtracting x bar from the observation that we've got xi here, dividing by the standard deviation, then we get this z score that's got a lot of really useful properties that we're able to use. So if this is hard for you to get the hang of, just bear with me. I'm going to give you examples of how we use this, and then in the lab work we'll kind of talk through what we're able to do with these z scores. So the z score is the number of standard deviations away from a mean. So if it lands here, if we have a value that lands in this part of the distribution where my mouse is, basically we're going to have a value that's between 0 and 1 standard deviations above the mean. Okay, so it's going to be positive. The same as if it lands down here where the mouse is, between this part, well, then we'll have a z-score which is between 1 and 2 standard deviations below the mean. All right. So the plot shows the probability of a value falling into any one of these intervals in the normal distribution. Okay, so we've got the standard deviations here, which are standardized across all of our outcomes, and then we get percentage values for where each value might be likely to land within the distribution. Remember that when we have a percentage value, that is going to be indicative of the future probability of any sort of value from that distribution being drawn, which lands in that particular area of the distribution. Okay, so a really nice technique that we were able to use to kind of understand the probability of a certain process. So, Ed, how do we use this? This is going over my head. This is too much information for me. Give me a concrete example. So we can find a corresponding z value for any value that we might have in the distribution, right? So how do we find the probability? Well, the old way is basically to use a z table in the back of your stats book, and there is one in the McGrew book that you can look at, or kind of the more fancy modern ways to actually use a computer to calculate this z score. Okay, so just for an example, let's run through an example where we will use this z score. So a make of car averages 25 miles to the gallon with a standard deviation of 3 miles to the gallon. What's the probability that I get a car that averages under 21 miles to the gallon? Okay, so what we have here is a make of car that averages 25 mpg, so that's going to be the population mean, because it's for that entire car manufacturer. We then have the standard deviation of the fuel efficiency here, which is 3. And then we have, well, we're interested in the probability that a car averages under this 21 miles per gallon value. Okay, so this is our this is the value that we are interested in, so the x value here. We have the mu value, which is the population mean, and we have the population standard deviation here, which is sigma. So we can put this into our equation. So it's going to be 25 minus 21, which is going to be 4 divided by 3, which is going to be minus 1.33. Okay, which means essentially that we get a z-score of minus 1.33, and then we need to work out what we're going to do with it. Okay, so I've provided the link here, which basically is a z-score and probability converter. And what I've done is I've basically put this minus 1.33 into the z-score box here. And this is going to provide us with an indication of the probability of all the values that are going to fall below this in the tail of the distribution, so the bottom part of the distribution. Okay, so you see here this red part focuses just on the bottom left-hand part, the negative part of the distribution, and what we're basically getting is 0.09 probability of those values, which is a 9% chance that any car that we're going to get is going to be in that bottom part of the distribution. Okay. There's lots of different examples for how you calculate these z-scores across the internet. So you can look at the examples that I'm presenting you here. We can look at examples in the book, or you can look at how you calculate z-scores on YouTube, for example, as a second way to kind of reinforce your understanding. There are also other kind of ways to think about this, right? So we've got that equation where we've got the z equals x minus mu as the numerator divided by sigma. We can rearrange that, okay? So we can rearrange that equation when we've got certain pieces of information. So just as one example, let's say that we can use the same mu and sigma values that we got before, but what's the miles per gallon value that represents the 95% mark across the distribution? Okay, so in other words, at what quantile does 95% of the distribution fall underneath that point? So here I've just placed an example. So this is a red bar which indicates the 95th percentile. And then we would end up having basically all of these values under here. And obviously this is theoretical based on the standardized score. But what we'd like to know is what the actual raw value would be in order to find that. So what we're interested in is the point at which all of the values fall below x. So, and that's going to be 0.95, okay? So that's 0.95% of the values, which means we need to find a z-score which represents the standard deviation for where 95% of the values fall beneath. Remember, this is a standardized score, so it can be applied to any distribution. And the way that we do that is basically we go to this z-score and probability converter. And this time I'm going to say, look, I want the probability of all the values being below this certain level. Okay, so 0.95. And when I do that, it's going to produce a z-score of 1.645. So this is the number of standard deviations that all of those values beneath 1.645 total 95% of the distribution. Okay. So when we do that, we end up with 1.65 equals x minus 25 over the standard deviation of 3, so which means that we need to rearrange the equation, right? So what we need to do is we need to shift the x value to the left and this z-score to the right, and when we do that, we can basically say, take the mean of the sample and then add the standard deviation multiplied by the z-score, and that's going to provide us with 25 plus 3 multiplied by 1.645. That's going to give 29.935 miles to the gallon, okay? Which means that 95% of the vehicles made have a miles per gallon average value which is below 29.935. All right, so I know that's complicated and I know that that's hard to understand, but just bear with me because we'll go through it when we're in the actual laboratory session. You just need to remember that the z-score is a standardized generalizable score, okay? So it's just saying it doesn't take into account the actual the underlying value. It's just saying the number of standard deviations that you would expect a certain value to be at relative to the mean, okay? And we can do this thanks to the fact that we've got normally distributed data. Again, we're able to use these 4 functions within R, so focusing on the density, the cumulative, or the quantile, or the random aspects of these different distributional types. All right, and I think I'm just reiterating here that these are standardized, and therefore you need to think of these in kind of abstract terms. We're able to use this to understand our probability focused across the distribution, thanks to the benefit of this data being normally distributed. Okay, we're almost done. 3 more slides, so you can take a breather. So I'm talking a little bit here about probability mapping because what we've just done before was quite kind of pure statistics, right? So it didn't really get into kind of the spatial science aspects of how we might use some of these stats. And the reality is that there is a lot of geospatial analysis that is really kind of built off some really nice statistical techniques. So I'll always use natural hazards as an example because they have a certain return period, like a flood or a tsunami, and we can understand that probabilistically over time, and then actually we could kind of map those probabilities onto different areas, right? So if you're thinking about flooding, then the probability of being flooded is going to relate to your altitude and your proximity to a body of water, for example, and those underlying characteristics that you have in a geophysical area. And we're able to actually use them to provide some sort of understanding as to the likelihood of an event taking place, which is basically how all of flood insurance works, right? It's pinned on this particular aspect. So in those previous examples, we were kind of limiting the probability to a single place, but the reality is that we can actually develop nice kind of heat maps which demonstrate the spatial variability of probability. So if you have continuous variables, you can map these across space. So here what I'm doing is I'm using an example of radio maps. So this is the probability of your cell phone signal dropping below a working threshold, okay? And you can see here you've got these green areas, which is where you don't really have a probability. I've got a very low probability of your signal dropping. And then you have these red splodges here, where you've got a higher probability of your signal dropping, right? And what these actually are kind of estimates for areas where you might have signal dropping relating to buildings, basically. So these green lines here are streets. You've got very few obstacles here. It means that the radio waves can propagate nicely from the cell tower straight to your cell phone, so you can just stream the data that you want. You're unlikely to be affected with interruptions. Same for calls as well. And then what you've got with these red splodges here is if you go into a building, then those radio waves are going to have to penetrate through maybe steel or concrete construction. That's going to take some of their energy away, and that's going to affect your probability of getting, a decent signal to do what you want to do on the internet. And therefore, you've got a higher probability that your call's going to drop or your data signal is going to drop. And you can look at this also in terms of isoline bars. This is an example here of peak acceleration for earthquakes. Okay, so you can see the San Andreas fault line running down here through California, and then you can see there's relatively little earthquake risk for quite a large portion of the rest of the country, right? So, I mean, it really depends on where you are geographically. So Texas has very low earthquake risk here, but obviously it has a much higher risk of things like hurricane risk. Thinking back to Harvey, which is probably about 3-4 years ago now, and the damage that was done then from extreme flooding, from storm surges and heavy amounts of rain. Anyway, you can think of this in probabilistic terms. So this map is just for earthquake risk, but you can also overlay these maps, which is quite nice. And you can, as a consequence, kind of look at the areas that have the highest risk to any. You can look at the highest risk that an area may face from all different types of hazards, which is kind of a nice way to look at it. So you can use probability maps in this way, where let's say you've got a distribution of outcomes, and you can maybe pick those areas that fall under or over a certain threshold. So you've got kind of the more extreme tails in a distribution, and then you can use these to directly map them across certain places. So let's just say that we only want to map those probabilities that are really high. So maybe we want to say these are the areas that are basically more at risk relative to other areas. So these areas have a higher probability of being flooded, and therefore we can just take those straight from this aspatial distribution here and plot them onto a map. Okay, great. We're almost done. I'm going to conclude this unit of the course now. The midterm exam will go up in due course. Focus on the assignment this week, and then the midterm will end up going along with those tests, those pre-tests, which are unmarked, which I need you to do in order to perform well on the midterm, okay? Let me know if you've got any further questions or queries. Thank you for tuning in, and I hope you have a good day, and good luck with the revision for the midterm. So, thank you very much. Goodbye.